Have you ever wondered how new aircraft are tested for vertical takeoff? You're in luck, because in this video we'll delve into the fascinating world of vertical takeoff testing and explore the rigorous process that brand new aircraft must go through before they can fly in this unique manner. So without further ado, let's get started. Before we get into the specific, it's important to understand vertical takeoff. Vertical takeoff, as opposed to conventional aircraft that require a runway for takeoff, refers to an aircraft's ability to ascend directly into the air without the need for a runway or a long takeoff roll. This is made possible by the application of cutting-edge technologies and engineering marvels. Let's now discuss the technologies that enable vertical takeoff. The tiltrotor system is one of the most widely used technologies. This system combines the capabilities of a helicopter and a fixed-wing aircraft, enabling vertical takeoff and landing while maintaining the speed and efficiency of a conventional airplane. Vectored thrust is another technology used, in which engines are outfitted with swiveling nozzles that can redirect exhaust gases to provide vertical lift. Vertical takeoff capability is critical in a variety of scenarios, including military operations, search and rescue missions, and operating in confined spaces. As a result, it's critical for aircraft manufacturers to thoroughly test and validate their new aircraft design's vertical takeoff capabilities. So what exactly is the vertical takeoff testing procedure? It usually entails a series of carefully planned tests carried out by highly skilled pilots and engineers. These tests are designed to assess the aircraft's ability to perform a vertical takeoff safely and efficiently. The ground testing phase is the first step in the testing process. During this phase, the aircraft is secured to a specially designed platform that simulates vertical takeoff conditions. The engines are started, and the aircraft systems are thoroughly checked to ensure they're in good working order. When the ground testing is completed successfully, the hover testing phase begins. During this phase, the aircraft is permitted to ascend into the air while remaining stationary, also known as hovering. Pilots and engineers carefully monitor various parameters during hover testing, such as engine performance, stability, and control response. If the hover testing goes well, the aircraft will move on to the next phase, which will include vertical ascent and descent testing. The aircraft gradually increases altitude while maintaining stability and control during this phase. The aircraft's response to varying throttle inputs, wind conditions, and other factors is closely monitored to ensure smooth and controlled vertical movements. Vertical takeoff testing is no exception. Safety is a top priority in aviation. During testing, manufacturers subject their aircraft to a variety of emergency scenarios to evaluate their performance under adverse conditions. Examples of such scenarios are engine failures, system malfunctions, and sudden changes in wind direction. Engineers can assess the aircraft's ability to handle such emergencies and ensure the safety of passengers and crew by simulating these scenarios. In preparation for the milestone first flight, an aircraft undergoes structural static tests, including a recreation of the aerodynamic loads the aircraft will encounter over its lifetime. Typical tests include maximum wing bending, aileron, and spoiler functional testing during wing bend, fuselage pressure tests, fatigue tests, and simulation of flight cycles encountered from takeoff to landing. The next step is certification testing, which will cover limit and ultimate loads in various situations, such as maximum wing deflection and fuselage loads, to understand the aircraft's behavior in extreme conditions. Fatigue testing examines how the aircraft structure responds to loads in repeated flight cycles, such as takeoff, climb out, cruise, descent, and landing. The purpose of fatigue testing is to understand the structural behavior of the aircraft throughout its life, as well as the inspection methods to be used in identifying potential critical areas while the aircraft is in service. To include a large safety factor for fatigue behavior, the A350 certification tests covered an equivalent of 3 times the aircraft's design lifetime. The flight test campaign for an aircraft is designed to evaluate general handling characteristics, operational performance, airfield noise levels, and system operation in normal flight modes, as well as failure scenarios in extreme conditions, culminating in certification by airworthiness authorities. Cold weather testing in Iqaluit, Canada, high-altitude evaluations in La Paz, Bolivia, and a hot weather campaign in the United Arab Emirates at Al Ain were all part of the A350's extreme weather trials. Furthermore, the A350 was the first Airbus aircraft to visit the McKinley Climatic Laboratory in Florida. The aircraft was subjected to various climatic conditions ranging from 40 degrees Celsius to negative 40 degrees Celsius in a climate-controlled hangar at this one-of-a-kind location. Water ingestion trials, when a significant amount of water accumulates on a runway, low-speed takeoff tests, and flutter and rejected takeoffs and landings are all part of the certification flight testing for a new aircraft. Furthermore, wake vortex trials are included in the certification process to measure air turbulence created behind the aircraft during takeoff. Certification flight testing for the A320neo family included validation of the aircraft's new generation LEAP-1A and Pratt & Whitney GTF-TM engines, including their lower fuel burn, environmental footprint, nitrogen oxide emissions, and engine noise, as well as aircraft handling qualities and performance, as well as system operations such as the autopilot. Certification is a legal requirement for all aircraft and engines. The EASA and FAA airworthiness authorities grant it. The type certificate, which certifies the initial airworthiness of an aircraft, is followed by an individual certificate of airworthiness, which allows aircraft to be registered in the country where they operate. Each Airbus operator's appropriate authority validates an aircraft's operation by releasing the certificate of airworthiness in accordance with their legislation. New commercial aircraft typically perform global route proving tours in addition to various tests and verifications. Airbus flew the A350 to 14 major airports on 4 separate trips, covering approximately 81,700 nautical miles in 180 flight hours. This also allowed future operators to see the aircraft in realistic service conditions and airport operators to become acquainted with the ground handling aspects. The Early Long Flights ELF program, which went above and beyond certification requirements, was another important aspect of A350 testing. To conduct these tests, a cabin-equipped flight test aircraft was flown on simulated commercial services with real passengers, Airbus employees, and actual airline flight crews to evaluate cabin systems under typical operating conditions. After the testing phase is completed, all of the data collected during the tests are thoroughly analyzed. Engine performance, aerodynamics, stability, control systems, and emergency procedures are all covered. Skilled engineers and aviation experts examine the data to ensure that the aircraft meets the necessary safety and performance standards. Following the completion of the data analysis, the aircraft manufacturer compiles a comprehensive report detailing the test results and submits it to the aviation authorities. These authorities, such as the FAA in the United States and the European Union Aviation Safety Agency (EASA) in Europe, carefully review the report and conduct their own independent evaluations. The aviation authorities have established specific guidelines and regulations the aircraft must follow in order to be certified for vertical takeoff capabilities. They examine the test data, run additional simulations if necessary, and thoroughly inspect the aircraft's design, systems, and performance characteristics. It's important to note that certification for vertical takeoff is typically required only for aircraft that are specifically designed for such operations, such as tilt rotors or certain military aircraft. Vertical takeoff testing is not typically performed on conventional commercial aircraft, which rely primarily on horizontal takeoff and landing. While ground testing and simulations provide valuable insights, real-world testing is also required to validate the aircraft's performance. During real-world testing, pilots, test engineers, and other experts fly the aircraft in actual operational environments to evaluate its vertical takeoff capabilities in realistic conditions. These real-world tests frequently include scenarios such as operating in high-altitude locations, extreme weather conditions, and difficult terrain. The aircraft's response to different loads, varying center of gravity, and emergency procedures are thoroughly evaluated during these flights. While ground testing and simulations are useful, real-world testing is required to validate the aircraft's performance. Pilots, test engineers, and other experts fly the aircraft in actual operational environments to evaluate its vertical takeoff capabilities in realistic conditions during real-world testing. These real-world tests frequently include scenarios such as operating at high altitudes, in harsh weather, and on difficult terrain. The aircraft's response to various loads, center of gravity variations, and emergency procedures are thoroughly tested during these flights. In conclusion, the vertical takeoff testing process is a meticulous and comprehensive series of evaluations that new aircraft designs undergo to ensure their safe and efficient performance during vertical takeoff operations. Through ground testing, hover testing, vertical ascent and descent testing, and simulations of emergency scenarios, engineers and aviation authorities rigorously evaluate the aircraft's systems, controls, stability, and response. Real-life testing further validates the aircraft's capabilities in diverse operational environments, while iterative design and improvements enable manufacturers to enhance performance over time. The ultimate goal is obtaining certification from aviation authorities, indicating that the aircraft has met all the requirements for vertical takeoff. We hope you found this exploration of vertical takeoff testing insightful and intriguing. Please let us know in the comments below if you have any further questions or topics you'd like us to cover.